have a ton of stuff, and if you stay over there, I'm going to stay over here and do this so you can hear me better, because you know how quick this needs to go.
Yep.
You got 2 hours to cram in 2 quarters worth of information this time, not just 1 quarter. And this is all the mechanical design piece of it. One of the largest chunks of your little packet for your reference. It's not any more than the overall FE exam. It's the same amount. It's about 4 to 12 questions maximum, or I'm sorry, 9 to 12 questions maximum in that section. But it just happens to be a whole lot of reference material because the formulas that you need are very prolific in this section. So you got to keep up with it and keep on track. So you can get a sense that we've got lots of things to work on, whether it's springs or threaded facet. What the heck? Who did that? Did you do that?
Is this on? Is it working? I should have just used an engineering spell to transform me to the class using a conversion of chemical energy into kinetic energy. Can you hear me?
Yes, yes, we can hear you. Yes, yes, we can hear you.
Okay, good.
Why are you here? I don't get it. We're doing the FE review.
Exactly. I need to give them context so all of their fast talking will make sense. So let me get started. Welcome to you all. We'll start by sharing a little story with you about budding engineers who wanted to become professional engineers and the journey they embarked upon to reach that goal. They started a long, long time ago in a faraway land of Buffalonius, where a cohort of Padawan engineers wanted to become famous engineers. Very famous within their profession. At the time, there was no clear path of yellow brick to lead them to their final destination. However, they did hear about stories and myths about the amazing engineering knights of the square table. These brave and intelligent knights had sworn to uphold the highest standards of mechanical engineering and worked to cram as much knowledge into the rawest brains of any Padawan engineers who sought their counsel. Now, these engineering knights included mathematical Sir Muradolat and maritime Lady Gal Abadi, engineering Sir Collins the Younger, materials Sir Bridge Villiers, biomed Lady Percival Hinachi, mechatronics expert Sir Leo Yoon, and of course, engineering wizard Melinda Anderson. That's how I know these engineering knights of the square table are real. Anyhow, the story goes that the engineering knights offered the Padawan cohort the sacred texts of test taking, which turned out to be the key to achieving their first goal. No, not any silly cup of the everlasting or chalice, but successful completion of their fundamentals of engineering wizardry. So, to get things moving, Captain.
Yes, yes.
Where are you?
Right
I
here.
can't see you.
I'm here.
Okay. To get this over with, quickly show them the sacred texts and review some of the information with them.
Okay.
Sound good?
Okay, deal. I got it.
Okay.
Got it covered.
Folks.
Jeepers creepers. Okay, here's the sacred reference and text he was talking about. This is what you all have to keep track of. It's those multiple pages of, this is just the mechanical design section, and what I was talking about, it's pretty extensive. A quick snapshot, and when we're taking a look at it, you're gonna notice some things you recognize. Right off the bat, it starts off with springs and all the different things about spring constants and how they work, how they add up, and their various construction. We'll talk about that in just 1 second, about the coils and some of the factors you put in there for the types of ends of the coils and how many of the coils you have. There's a whole section on bearings that are going to come up in a moment. You need to remember that bearings had load ratings, they had durations of or probabilities of failure, which associated with their longevity, and we have also fit associated with bearings and how they come together. Power screws, if you remember, power screws is another name for an Acme thread or a square thread. Power screws are things for power transmission, less friction than a regular thread. So you have a couple of formulas that are associated with how power screws are applied, how much force, torque, and load it can handle. There's a whole chunk on gears, there's the axles and shafts a little bit right there. You've seen most of that already. But there's a whole chunk on gears. Now here's where things start getting a little mucky, because not only do you need to remember the basics of gears and how the gear teeth work and mesh with one another, but gear trains, and how you can take an input of one transmission force and get an output on the other side that's different, and its rotational speed is different. So that's what all this section is about. This is that gearing nomenclature. Remember pressure angles and the contact force that shows up in gears. You've got to do lots of those. Threaded fasteners is a whole separate section, otherwise known as bolts and screws. This is trying to clamp stuff together and knowing how much load you can put on a bolt of a certain size with a certain torque on the nut, how much you're going to keep squeezed together. All of the problems up to this particular point are actually very straightforward. You just need to remember or find the right chunk out of this section to use the correct formula. Because the problems are not complex, they're pretty quick, just like you practice in the other sections, because you only have about 3 minutes to whip it out. But you've got to be able to recognize where to go, what the terminology is asking you to figure out. Materials of gears and their ability to support different load forces on there, or threaded fasteners. Bolts and rivets. Not a lot spent on this, not a lot of time we invested in it, but the point here is every one of these is strictly a free body diagram. So if you recognize that's the simplicity of these problems, then they're pretty straightforward. You just need to recognize what type of failure might occur with that type of loading and how much you can transmit with that type of circumstance. There's a whole section on fits and shrink fits. So it's very straightforward again, knowing what the formula is. Once you see the formula and you kind of go, duh, I see exactly what they're asking me to do, you can either figure out the interference or you can figure out the required material property. You fill in the blank is essentially what I'm saying. There'll be something missing out of this equation which you need to solve. And those are all the values that go along with it. You see we're only halfway through. These are the limits on fits, excuse me, the definitions that go along with fits that you need to recognize and recall. The tabular formats that define the types of fits, whether they're loose running fits or snug fits or tight interference fits. So if they gave you a code, you'd know what it's telling you, and then you'd know which formula to apply to that circumstance. They also ask a lot of questions about, given this size hole, this size shaft, what would be the maximum interference? And so you need to be able to just use any one of these simple formulas here, but apply the right values to it to make it all work. Deviations in the shaft. GD&T is the other part of this section. Geometric dimensioning and tolerancing. Now we've talked about that a little bit in 315. Everyone in 345 we talked about it in some form or fashion. You need to reference these items. The way this is going to come about is they're going to give you symbols and you need to figure out what they mean. You have to remember to go to the table, to go find the definition, so you can then translate it and give them an answer about what it is they just asked. These terms are pretty important, which we'll review in just a moment. Things like least material condition and most material condition and so forth. Here are some of the symbols that show up. Here are some of the other symbols over here that show up in the GD&T reference. And these are what they mean. So you'll be able to pick the right answer on the multiple guess. Here are more symbols that go along with it. This is for columns, which we already talked about in the other class associated with Euler's formula. Some static loading theories, again, which we talked about in the mechanics and materials, which is already in here. And the loading theories, endurance limits, which we already talked about. And this is the one section here that we won't talk about, but it shows up in a different section, either in the dynamics or the mechatronics. These are the linkages, the kinematics of linkages, where you essentially have links and links like this. And you're trying to figure out what the angular displacement is in different places and that sort of stuff. So that's what those problems are all about in trying to figure that. I'm not talking about those because we don't cover those in this particular module ourselves. That's covered in one of those other two modules, but it's part of the data in this section of your handout. That last page is symbols for hydraulic power. We don't do a whole lot of that in our programs here, but this one page is strictly the type of things they may ask you, and they simply put it in the form of, if this symbol shows up on the hydraulics that you're using, what would that mean? And you have to be able to translate that, figure it out, and go find the right item. So it's pretty easy. There's not a whole lot of studying on this one. Like I said, we don't go into a whole lot of hydraulics for our purposes. That's the sacred text right there. Done. I can walk out right now because you're all got it all. You just read it all and understood it. If you'd like me to stick around a little longer, I'll try to give you the rest of the background that gives you a reference to all those materials. You want me to stick around just a little longer? Deal. Okay, so let's keep flying through this. Obviously, I'm going to touch on springs, I'm going to touch on gears, threaded fasteners. There's the symbol for GD&T. Essentially, that's everything you just saw on that sheet with the exception of the linkages and the stuff on the hydraulic power. So let's sober up a little bit. Let's have a few nightmares about the stuff that we did cover that were like, oh my God, those problems. It's kind of like bringing back thermodynamics. Okay, but this is not thermodynamics. It's way easier. First off on the hit list is threaded fasteners. Easy one to understand. Terminology is the one thing that kicks people's butts on this one, is to remember what a major and minor diameter are, what pitch is, and how it all sets up. That image right there is probably the single most powerful thing you can try to remember or memorize, because it makes the problems way easier when they ask you a question. Don't forget that that pitch is the distance between the threads. Major diameter is the size of the hole you're going to bore to put this bolt through, which means it's the outer or maximum diameter on the overall unit. Minor diameter is on the inside. Pitch diameter is that theoretical difference between the two. You see the dashed line right there. That's based on the contact angle. Remember on gears where we talk about that contact angle, that's where they get the same sort of nomenclature when you're talking about something circular and where that contact point is. We call it Unified National, the Unified National Standard. So Unified National Coarse, Fine, and Special. The problems you'll get won't necessarily get into a whole lot of detail on this, but they may use that terminology in the question to say, given a UNC thread, and then they'll give you all the specs on it. You go about your business. All that's doing is giving you some context before you solve the problem. The key area, though, that you need to keep in mind is that first item up there where it says the tensile stress area. That's the area, the unthreaded rod, of the same tensile strength as the threaded rod is. We use that when we start talking about load forces on bolts, because that's the solid piece that's connecting the overall bolt together. So you've got to keep that in mind for the next items that you're going to be messing around with when you do the formulas. This is just a quick explanation of that coding. If they do give you a bolt, that's the technical formal code. Well, the first number on here happens to be the major diameter, so that's a 1/2 inch. 12, that's the threads per inch. This will tell you the type of threads, coarse. 3 is the tolerance, which is a class of fit. A is whether it's an external or internal, meaning it's a bolt or a nut. LH for left hand or right hand. And that's the standard nomenclature that you'll see if they specify something on there. This is the complement for metric. So the metric starts off with a big M. Okay, there's the dead giveaway. Oh, metric, good. It's an M10, 10 millimeters by 1.5. 1.5 is the thread pitch, not pitch, but thread pitch in millimeters. This is the other one, though, that is more important in the bigger scheme of things, because this is the one where they're going to ask you to do some formulas and calculations, which is the power thread, the power screw. This is the square thread called Acme. It comes mostly in the square thread shape like this. Some of them are ever so slightly tapered, but predominance of the problems you're going to be given are simply they'll call it a power shaft or a power thread like this. And they have relationships between obviously the diameters, but the depth of the threads themselves, and you can see the little table that goes along with it to give you some reference. This is where things get interesting, because a power screw, because it is rectangular and not triangular, on the helix, there's less friction. That's why power screws work so well, and that's also why power screws are so accurate. So when you use them for minor adjustments or to lift big things or lower heavy things, that's why they work. Less friction on that. There's only one angle to deal with, and that's the angle that's going downhill on the helix that's parallel all the way through. Whereas a regular thread, the Acme thread, has a second angle, so that's what causes the extra friction, and the power thread, it doesn't work quite the same way. So as a result, we have formulas that are already pre-made for both raising and lowering loads. So whether you're trying to lift it or drop it, you've got a set formula. If you substitute in the simplification for torque, you have two standard formulas, which you're going to find, those red blocks are the same formulas that you find on your cheat sheet associated with lifting or lowering a load. There's an efficiency associated with it too. That efficiency, based off the torque over there, comes out to a ratio of the two torques between the regular friction and zero friction efficiencies, like any other efficiency, the ideal compared to the real. The only key here is, you'll notice, I use the E efficiency, your cheat sheet uses N. Same formula. They just had a different value they used right here, efficiency-wise. So you may be asked, what's the efficiency of this thread? Here are some specs. Or you may be asked, what would it take to lift the load of this mass? Power threads. Other threaded things. Quick note on threaded fasteners, hexagonal headed bolts. There's a whole set of tables if you go back to Shigley and 829, which talks about the relationship to the size of the bolt, to the length of the bolt and its diameter. Nothing you need to memorize, but recognizing some of the setups when we start getting ready to talk about threaded fasteners and holding things together. So the general relationship for thread lengths are based on those two formulas right there. They tend to run, you can kind of see there's ranges when the length is less than 6 inches or greater than 6 inches, and so forth with the millimeters. That just gives you an idea what the diameter will be compared to the overall length. Again, not something you need to memorize. This is context so that when you start getting ready to do the problems, it kind of makes sense what they're asking you and what it's based off of. So nuts, excuse me, are the opposite one. Again, that shows the general sizes of the nuts. That's just context here for a second. Here's where we start getting at the problems they're going to ask you. So when you take two materials together, and in this case you're using a bolt and nut combo and you're compressing them, how much load force have you put on there? How much force could you put on the plates if you were to pull on them, for example? So that's where we need to start talking about that. There's a grip length L, which includes everything that's being compressed, including washers. Now, washers simply add this much additional calculation to any of your problems. Kind of a toss-up whether they will include them in the problems or not. Most of the time they simplify them and just say it's a bolt and nut without washers on there. But if they did say washers, you just include it in the overall length, the grip length that you're talking about. For tapped holes, in this particular case, this is a screw. Remember when you stick it in and it doesn't have a nut on the other end, we call them screws, theoretically. Don't forget that the grip length that we're talking about is going to include this particular material, and you can see that's the different ratios for that. So here's where we start getting into it. The thing about bolts and threaded fasteners is they are essentially a giant spring holding everything together. So if you remember when we went through this, we used theories of springs, or if you want to, resistors, same concepts, where you add springs in series or springs in parallel, resistors in series, resistors in parallel, that sort of thing. We used that sort of concept because you understood it and said, well, let's apply that model to a bolt. Because theoretically, a bolt, let's just say it's steel, kind of elastic at room temperature in a certain way, so we can apply that spring constant concept. Anyhow, we put these all together. We use a K for that spring constant to talk about it. So now we have an overall length, we have a known material, we can say how much force this spring is putting on it. That's how much load you're using to cram the entire sandwich of material together. And that's where you get these formulas, these three different formulas. The B is for the bolt and the threading associated with the material that you're clamping together. And this is how you can add up all the various spring constants to get the bolt's overall spring constant, because you're talking about what the resistive force is from the different parts of the material that you're sandwiching together. Now, when you look at the part side of the equation, we had to do that funky math where we talked about the frustra. I love words like that, because you kind of, where did that come from? Well, it came from Latin. You mean the Greeks and stuff? Yeah, they did this sort of thing. No, not really. They have these pyramids though. That's the frustra we were talking about. And there's a force distribution that's in the sandwiched material. All right? There's a maximum load at a certain point, a minimum load. We used that to do the analysis to figure out what it was, so we ultimately could come out with what's called the spring constant for the member, or the materials being sandwiched. So you won't need to deal with that chart, but this is the background of where that comes from. And you'll notice it's got the modulus elasticity, which is the material that's being squished together. And you've got these factors, this A and B factor that are in there. Where does that come from? Well, we put it in tables. So for steel, there's Poisson's ratio. Remember, that's the shrink to stretch or expansion to squish ratio. We also have these two values already predetermined, these A and B values that you put into this formula to get the spring constant for everything you're smashing together. This is fair game for you on the exam. All right? You noticed in your cheat sheet, there were a couple of these tables in there. They'll do it two ways. They'll either give you a problem expecting you to use this formula, and they will state the A and B in the equation or in the question, or they'll simply tell you what the material is, expecting you to use this and going finding it in the table to get those two values. Yes?
Would we be expected to do a frustum problem?
No,
No.
you won't do the full
I
frustum. That
remember-
was theoretical basis to get to this point
I
right
remember
here.
those took like half an hour to do.
Yeah, no,
Okay,
no
okay.
frustum.
So just go straight to the tables.
This is where you're gonna go. This is the formula you're driving for, and you're simply gonna be asked about the nature of the circumstance, whether it's the material or the bolt itself.
Okay, thank you.
And these are the formulas they're expecting you to use. Oh yeah, shake it out. You know the routine. I mean, not every other professor does that with you? They just talk the entire time? Oh, I would go nuts. Turn around. Makes your feet work too. Balance. Yep. All right, touch your nose, one hand, touch the other. No, that's wrong test. Sit down. Don't do that. I don't want to know the answer to that one. All right. So, real quick, threaded example to see what I'm talking about. Two plates going to be mashed together with a washer faced 1/2 inch 20. You can see what I'm talking about here. They can sneak in that UNC nomenclature there. You can see they snuck in a washer. They've got a grade on the bolt. Don't worry about that because that's something they're going to give you in the overall problem. But we can figure out the member's spring rate or stiffness of the plates, and we can figure out the bolt's spring rate or stiffness. We just use those two formulas, the member Km, the bolt Kb. So you go through the quick math of figuring out the dimensions. If you know the dimensions, you can just go back and use that Km formula, put all the numbers in there with the A and B's that you get off the table, and all of a sudden the member stiffness is 14.9 times 10 to the 6th. If you did the same thing for the bolt, you need to make sure you're adding up all the pieces in there, all right? The threaded length, the length of the unthreaded portion that's in there as well, the unthreaded portion and the part of the grip, major diameter of the area, tensile stress area right there, A sub T, put it in the bolt formula, and you get 3.69 times 10 to the 6th. So neither of those problems are complex. They're very straightforward. You just need to write down all the things you know. Okay, that's the other trick to a lot of these problems is as you're reading them off to the side, if you write down the numbers of what you know, and if they tell you what the material is, you know things like modulus elasticity. They may not have given it to you, but you can write the letter E next to what you know, because you can look it up in the tables we've given you in the other parts of your exam section. So once you write down what you know, it's a good hint as to what formula you're going to need, because the next thing you write down is what do you try to find? Write down the variable for it. Ah, I'm looking for the stiffness of. Then you just start plugging in all the numbers and go. Yes?
Are they gonna give us the thickness of the washer? Or are we
They
gonna
could. They may not give you a washer at all, but they will if they give you a washer.
So we wouldn't have to look that up in a table, because I remember from Shigley, there's different types of washers.
There are, and
depending
that's
on-
why I said back here, this SAA grade 5 and the washer that was in here like this, they're gonna simplify it and give you those, because they're not looking for anything to go rummaging through to find out. They'll just say an 1/8 inch or 16th inch washer.
Okay, thank you.
Okay, that was that bolt. Bam, so there's the two stiffnesses. If you tighten a bolt, you're gonna put a torque on it. That torque is gonna put it under tension. There's another formula that's set up. When you do the math and the theory to get the torque out of this whole thing, you're talking about the angles and the threads and everything else. That's what all this ugly was. We take all of this ugly, we give it a letter big K, and we replace it in the formula, and that's the simplified version that's on your cheat sheet. Trick, you need to go find the K. There are tables in your cheat sheet that give you the K value for given materials. If the material is not given on that table, you're gonna use 0.2. It even says that in your cheat sheet. Use 0.2 for all others. So then you stick 0.2 in here. And the rest of the problems are easy. Static factors of safety. So just sitting there, not doing anything, you've got an axial stress, a yield factor safety, load factor safety, and a joint separation factor. Not much to tell you about these formulas except plug and chug. So be very explicit in understanding what the question asked you, and simply use the right formula to figure out what the load factor of safety is. Done. Fatigue stress. Now that's taking something and putting the bolt under a constant flexing, okay? Over and over and over and over. Not a good thing, obviously, but if I have an alternating or a mid-range or average stress, depending on which one you're given, you have a set formula based off of the maximum and minimum forces and that area of the bolt, the effective area of that bolt. And you'll be able to figure out what those stresses are. Yes?
So for these, are they also gonna be plug and chug, or might we have to solve for like one of the components first?
You might have to solve one of the components. They may give you, that's where either free body diagrams or the geometry of the circumstance, that's the only intermediate step that you'll have to do before you go to this particular point. Okay? And just as context, there are lots of those failure criteria, Goodman, Gerber, Soderberg, who made all of these different lines that we came up with on the mean stress to the alternating stress combinations. Predominantly, we use the Goodman for the ability of it to be a good estimate. Again, this is just context because we use the Goodman line to put it inside the formulas to figure out ultimately that right there, which is the fatigue factor of safety. And these are based off of a constant preload, that line on the earlier diagram for the failure criteria point. All we did was use their failure criteria, the Goodman. Theoretical, we did lots and lots of formulas, we simplified them down, and that's the end state right there, where you can see the ultimate stress and the right here, this is what I'm trying to say, these right here. Okay? That's for a fatigue circumstance. Those are a little more complex, you won't get many of those. They won't go quite this far, but that's one of the formulas on there, so it's legitimate to know and to look at it, yes?
You did wanna ask a quick question. If we're asked a question like this, would they refer to it as preload, or would they just say the bolt's been torqued to insert spec? Just cause I know it's the same thing, but I just didn't know.
I can't speak
Okay.
uniformly, but pretty much I've seen this sort of statement
So
on
they'll
there,
say
because
preload.
it's been preloaded too.
Okay.
They're
Okay.
just trying to get you to think in that direction and know that that's what you're working on. If you get the repeated loads, because if the external load goes from 0 to a maximum, you can take this big ugly back here, simplify it, because P minimum becomes 0, so now your mean stress right here simplifies down to this formula. If you go to the constant preload line between all of them, and know that the slope has 1 on there, we've simplified the formula even further. And that's when it goes from 0 to maximum, so it's only loading in one direction. Again, those are just the curves that we use to get those particular values, and you can see the relationships between the curves based off of those values over there. But if we repeat the loads, depending on which one you use, you can either use Goodman, Gerber, or the ASME elliptic. It's the only 3 we typically use. These 3 are on your cheat sheet, and the problems would be explicit as to what they're asking you to use. They'll say using the Gerber method, or using the Goodman line. That just means grab the right formula before you do the final calculation. These are the simplifications for Goodman. What's nice about these is they make the calculations way easier based on the ultimate strength of the material, and those are material properties that you're given. And ultimately, you want to ask the question, is your bolt going to break? You need to always check the yield strength based off of all those curves we just had back there, and that's what you get as the simplified formula to check the final stability of the bolted assembly. Stand up, take a break. See, this goes fast. There's no messing around. Take your arms out a little bit. I like that, digging it. I found my jacket just the other day too. With all this crazy weather, I was out trying to clean stuff up, was gonna pressure wash something, and I said, wait a second. Walked back in, I found the pants that go with it too. And so I was trooping around my house in my old camouflage Gore-Tex. Hose with a pressure washer, hose stuff
Hard to
down.
see, huh?
Ah, you couldn't see me at all, just saw a pressure washer moving in the air. Oh hey, bolts, or rivets. The big picture here is understanding the differences and picking the right one, okay? So sometimes they'll give you this image in the problem, sometimes they'll explain it, and you need to understand which one you're looking at. These are the different failure modes of putting a couple of plates together, drilling a hole, and putting a rivet or a clamp of some sort, like a bolt through it, and knowing what sort of load force you're putting on there, and picking the right formula to give you the answer you're looking for. So whether you are, you've got the direct axial load, or you've got some shear force load that you can see here. That's the shear force tearing that occurs across many of them. You've got the tensile tear out that's going to occur depending on which deformation mode you're looking at. That sort of rip that occurs. So you can see the formulas that apply. They're just right in there in the image. That's really the big picture: is pick the right failure mode and then pick the right formula. If the loads are not even, and you've got a shear load on there, so really what I'm looking at are these bolts with this bar that's attached to these two angle irons, these L angle irons here. I've got some sort of load, distributed load, but it's not distributed completely across the beam. I need to figure out what the load is on all of those. How am I going to solve this? Say it out loud. This is on the problem, this is on the test. You got 3 minutes. What?
Reference sheet.
You got reference sheet and a free body diagram. Regardless of what the bolt pattern is, given the load, you simply put together a free body diagram. And those are the X's and Y components of the force loads on there. It's the sum of the forces, and then the sum of the moments. So figure out your X, Y positions, and you can figure out what the overall loading is on that bolt pattern, whatever it happens to be. This one's fair game. From the standpoint that they'll give you a bolt pattern and simply say, what's the load? So you'll go through this process of doing the free body diagram for the sum of the forces and sum of the moments, figuring out what it happens to be across all of them. If it's symmetrical, then you can make some cheats along the way and add them up. So if the bolt pattern is like that, right there with 4 bolts with a given load, do the free body diagram, sum of the moments, sum of the forces. There's the diagram, so you can see the points, and you'll recognize some symmetry right off the bat. Fully fair game. So, in this context, this problem would ask you about the load forces on the bolt, and then the second part of that question would be going back 3 slides and using the right shear force, because now you found the F on that bolt, or the total F on that bolt. So you can go back and use the shear force equation to figure out what the shearing force is in that attachment. Yeah, some of the forces, some of the moments. All I've done here, this slide is just a simplification of several slides where we've just done the math already and put it all together. You get another break. Looks, threaded fasteners, we did a power screw. We've already talked about the load forces associated with the bolts and the free body diagram. I think we're ready to move on to a new topic. Yeah? Okay, sit down, move to a new topic. Oh, springs! Woo! There we go. Springs. What do springs do for us, by the way?
Store energy.
They store energy. That's the super single biggest thing you want to get out of springs. So when you talk about springs, it's about how much they can hold in their load. Now, if you remember back, in order to get the spring stuff taken care of, we had to kind of dissect the spring a little bit to understand what's happening there. Now, in a coil spring like this, am I just doing straight compression on the metal? What am I doing?
A little bit of torque too.
I'm twisting it actually. Physically, in a coil spring, I'm physically twisting. It's a torsion spring mechanically, because when I push down on this point on the spring and I'm compressing those coils from one coil to the next, I'm essentially twisting that wire all around and putting a torsion on those. That's where the spring force is really coming from, is twisting the wire. And the cool thing about a coil spring is, instead of having just a long rod and twisting both ends, I can coil it all up and put it in this much space and get the same effect as squishing it this way as I do trying to take this rod and go like this with it. Kind of like, whoa, light bulb. I get it now. All this time, I didn't realize. Yes, so they're absorbing energy or storing energy for us, and we're doing it by twisting that spring. And you can see right here in this little image where we've kind of cut it in half, in the center of the piece here, is that load force, while it's actually against the helix, it's twisting the spring. That's why you're going to notice a lot of pi's in our calculation. Not apple pies, but pi is 3.1415 and so on, because we're doing the math of the circular spring. So here's where you start getting into it. This, by the way, is the collective diagram of load forces on the spring, and this is that torsion, the end state torsion that you're getting inside the material of the spring. You have both a torsional shear and a direct shear. You got the maximum stress is on the inside fiber. So the inside fiber right here, the intersection, is getting the most load on a spring. And those are the classic formulas that you're going to need in order to figure out what's going on with the spring. By the way, E, you know, G is the modulus of rigidity, J is the polar or second moment area of the diagram itself. And there you go, there are the pi's that start showing up in the different formulas. All right? So this collection of formulas you need to keep in hand, because they're going to ask you a whole variety of questions about springs. Springs are like a big chunk of this. Loading of a spring and how you're going to put it together. So when you work out all the formulas and put it together, we get something we call a spring index. There's a correction factor for the shear and the maximum shear stress. Given formulas. This is, you don't need to redo these. These are given now. You've already gone through the course and did all the theory to get here. This is what you need to do to apply to a spring in order to incorporate the spring in your design later on. So you need to kind of keep these sorts of things in mind and use them going forward. You need the spring index inside the correction factor right there. That's why you had that spring index to begin with. Now, when you compress a spring, we're going to use Castigliano's method of energy. Doggone it, now I know why we talked about Castigliano all that time in the class, because that formula actually helps us. It's talking about energy balance. Wow, that's what you did in thermodynamics all quarter long, was the energy balance. Same applies mechanically to a spring. I'm going to put some load force into it, energy into it. It's going to store in the spring, so I just balance out the equation from one condition to another to figure out how much energy I put in there. So that's what all of this stuff was about, and these are the classic sets of formulas that go along with it that we saw earlier. So if that's the case, I can use it to figure out the deflection. That's a very fair question. Given a spring, all the specs on it, how far will it deflect under this load? Classic. That much. Spring constant, or the spring rate, classic formula right there. That's another question they get asked you. What is the spring constant for this spring given these circumstances? Very straightforward. You just need to figure out what you're being asked, use the right formula, figure out what's missing out of the formula to solve for it. You do need to keep in mind the ends of the spring. Whew, for two different reasons. This is the first one, is how the load is being applied physically to the spring. In some cases, we just cut the wire perpendicular to the axis of the wire itself. In some cases, we grind down the end until so they're all flat, completely flat, but you'll notice I've cut a spring, a part of the wire, in some sort of big, smeary, spirally flat cut. That's what gives me that flat end. In others, instead of just having the end loose, I have that end loose, but it's on an axis that I can keep track of. It's called squared. And in this case, it's squared with the axis of the spring, not with the axis of the wire, like up here. Notice this last helix, we flattened it out. Instead of allowing the helix to continue up, we went and bent that last little piece. So now the flat end is on axis, and that little part is now, that part of the wire is flat. And over here, it's just a left-hand ground, similar to what you had up in the other one up there. It's a plain ground end instead of the squared ground end. So up here, this was bent the same way and then flattened. This was left like this and then flattened. All four conditions have different circumstances in their spring ends that you need to add into the formula to make it accurate when you do the final calculations. So you can see plane, plane and ground, squared and closed, squared and ground. And depending on the number of coils, or the number of end coils, you've got a pitch formula and a free length formula. This table is available to you. You just need to find the right one when they ask you that question about, for this given spring, for the deflection or for its capability and load, go grab, and they give you end conditions, that means you're gonna jump into another table. As soon as they start talking about the end conditions. That's one state. The other one, let me talk about stability. So, sometimes springs are unstable. So you remember that part of the conversation where we take a spring and we start to compress it and it pops out the side because it bends, it goes wing. That's an unstable spring. A stable spring, you compress it, it stays together. So that has to deal with the size of the wire and the diameter of the overall based off of the length. And that's the criticality formula right there for determining whether your spring is going to be exceed the critical limit and pop out the side. Dangerous springs that way. With that, there's a stability or a slenderness ratio right there, effective slenderness ratio. That's what this formula is. The alpha is the end condition constant. So you need to go back to the other table and get the alpha associated with the end conditions. And that's how you deal with stable springs. Those are the constants right there. And this is like a column. Remember, columns are pin-pin or pin-free.
Yes.
Okay, thank you. I thought we talked about that. The same thing applies for springs. You generally have those same four conditions. As a result, whether you're grabbing a hold of the spring on the end or the spring is loose on the ends will partially dictate whether that spring will be stable or critical or stable. So that's where this alpha factor comes in. Just like the columns, you'll notice these numbers are actually the same. Look at all the connections you're making. So if you go back to the stability formulas, that alpha right there comes right from here. So you need to know what the end conditions are of the spring before you talk about whether it's a critical spring or not, or whether it's exceeded its criticality factor. So there's the absolute stability occurs when the ratio is greater than 1, and for absolute stability, L0 right there, that's for steels, that's overall stability. We've taken out the E and G and done it for you and simplified it. Those formulas are available to you. If they say you have a steel spring and you're talking about the absolute stability, the length for absolute stability, that's the formula right there. There's the diameter, there's the stability factor. So you can go back one page, and get the alpha. Okay? Springs, lots of spring stuff. You're gonna have lots of spring stuff. So these are your spring formulas. You have access to all of these. Again, you just need to remember what they mean and which one you want to use based off the question they're asking you. These are the tables we just showed you, and you have access to those tables and those formulas. Now you see why you have so many pages in this section. Because you've got lots of formulas to muck around with. A few more associated with the tensile strength estimations on there. And one thing I didn't talk about that you're not necessarily going to get asked about because it gets kind of complicated is the set. Anybody remember spring set? Yeah.
It's where you load it before so that it deforms a certain amount, but you're trying to have it be where it's, I can't remember 100%, but I remember set being where you're loading.
It has a preload. It's like a bolt with a preload. It's a spring with a preload. So before you put it in use, you've already compressed it and given it sort of some potential energy that's already built in. So when you put it in its application, it already wants to shove it back up again from its initial condition. So you give it some compression on there to do that. So set starts to show up when you stick it into the formulas here as a compensation factor. But without that, these formulas I hear before set's removed, you can come up with the shear yield strength of that spring based off of a percent factor times the ultimate strength. And there's the ratios you're going to use for the various wires. You get this table right here. It's in here. This table is in your cheat sheet. Because it's another classic one, is what's the yield strength of the spring. like bolts, you can put springs and have them fatigue. If you have an alternating mean force, that's the mean force over the spring's duration. If you have alternating mean stress, those are the shear stresses that are in there. You can use those formulas to figure out what's going on. Another type of spring that you're going to get asked about is not the coil spring, but it happens to be a torsion spring. Now, I already told you that a real coil spring really is in torsion, but we don't talk about it in that sense because you're compressing the spring axially. A torsion spring, like you see right here, is like a clip or something in the door, and it's designed to actually take that coil spring and tighten the coil or let the coil loosen when it relaxes. So in this case, you've got a slightly different set of formulas based off of the geometry of the spring moving this way rather than this way. That's based off of the movements of the spring. That's what this ends up being, number of turns that you have in there to be able to deal with a certain circumstance and how much you're going to deflect it. For a torsion spring, there is the spring rate, and the spring rate is related to the torsion, the moments it's on there, and the angle displacement. Okay? So that's the formula you're going to end up using if you see them talk about a torsion spring. There are stresses in torsion springs just like there are in regular coil springs, and those are the formulas you're going to end up using for them. That's the right there, you can see the stress correction factor that's going into the shear stress, or the normal stress, I'm sorry. Here's the normal stress final formula right here, K sub I 32 FR over pi d squared, and that S sub Y, you're given this table. S sub Y for music wire, carbon low alloy, or hard steels, and or non-ferrous materials. And you'll use this prefix right here to figure out that S sub Y. Remember that percent factor of 3 slides ago? There it is in use using those factors right there. So that gives you the S sub Y. Woo! Go ahead, stand up, take a break, ask a question, take a drink.
Music wire, that's like what, guitar string?
Yeah, or piano wire.
Okay.
Yep, and it's a low, usually a low carbon 1080, probably maximum what it comes in.
I remember spring set differently. Is it being like to do with how it's manufactured?
Right.
Checked it because it's not pretty much this. When you have a new spring and it's initially closed,
Yes.
there's going to be some distance that it doesn't.
It gives. That's right, and it's based off material property. That's why I say preload. What you're doing is you're taking the material property, knowing what the material property is of that. So, this problem is way longer than you're gonna get, but you could get any one piece of this problem. Is why I wanted you to take a peek at it. So, you got a helical spring, number 16 gauge music wire. There's that hint that it's that music wire. You're gonna look at it for the table. Outside coil diameter, 7/16 of an inch. Ends are squared with 12.5 turns. So now you can see I'm gonna jump to a couple of tables right off the bat. Because when you see things like the size of the spring, that the ends are squared, I've gotta go look at the conditions of the spring and make sure I pick the right factor that's in there. I know how many turns, and I know how many turns that are in there. So now I can figure some other stuff out depending on what they're asking me. In this case, what's the torsional yield strength of the wire? What's the static load for the yield strength? What's the scale, that ratio? What's the deflection caused by a load, given right here? Estimate the solid strength of the spring. What length should be to ensure that when it's compressed solid and released, there will be no permanent change. Given the part above, is buckling stability a problem? What's the pitch of the coil body? So a couple of these are relying on a previous step, but you could probably do any one of these and be asked one of those questions along the way. When you start going through the math, it's pretty straightforward. Now, all of the tables I'm referring to are Shigley tables, but you're given these, or you saw tables I already just shown you on previous slides of where these numbers are coming from. So I know what the overall type of spring is, so I know what the diameter of the spring. Given that particular spring's material, I know what the A is and the M is. I could put that in my little formula and figure out what the ultimate strength, 324 kPSI. If I know that, I'm going to that other table that said for music wire, it's 45% of the ultimate strength, so the yield strength happens to be 146. Done. Those were all tables you were already given in your cheat sheet. These are just the Shigley equivalents of those tables to go find them. So, you're gonna use that information here subsequently. Static load, yield strength, well, I need to know the mean coil diameter, that's it right over there. The spring index, C, is the ratio between this and this. The stress concentration factor, based off of this spring index now, I can calculate it, I can put it in the formula. We gave it to you a few slides back there ago, that's the concentration factor. And replacing shear stress with the ultimate strength, because that's when it fails, solve for the F, because it's the one thing you don't know. Solve for the F. So you know the yield strength, we got it from the previous slide. You just figured out K sub B, you know D up there is 0.4, you put it in there and 6.46 pound force. So that happens to be the static load at yield. Again, you knew to do this substitution because they said static load at yield. Coil springs are in tension, so there's a shear stress. Replace shear stress with the ultimate shear, the yield strength, and that's the point at which the spring's gonna break. Don't get caught by that last step. It's not a trick. Just when they say what's the load at yield, you can take any of the shear or other stresses and put in the ultimate stresses, or also ultimate strengths in there. If you're trying to do the scale of the spring, again, number of turns was 12.5. You subtract off, when you go into the table for the type of spring that I told you, the ends, you're gonna subtract off 2 to be able to give you the total number of effective turns, because the ends aren't effective depending on what type of end configuration they are. I probably would be given this, but you can also look it up if they ask you to look it up. So the scale of the spring, this is that formula right here, scale of the spring, we're just now plugging in the numbers and coming up with 4.13. If you're trying to look at the deflection, I'm looking for Y, I'm looking for some sort of movement. Already gave you a simplified formula along with a bigger one. Force over K, well, I just figured out K, it's 1.56 inches. So now I know that spring moved 1.56 inches. So you can see what I'm talking about. Any one part of this problem is fair game on the exam. A couple more. What's the solid length? Well, I gave you the solid length formula right there. That was on that previous slides as well. It's on your cheat sheet. So you simply put in those total turns, not effective turns, plus 1 times the effective diameter, you get a 1/2 inch. What's that? That means when you compress that spring completely and one coil touches the next. No change in the free length, that's the L sub 0. This is the critical length or buckling. So the buckling equation, you know L sub 0 is 2.06. We know it's less, L sub 0 is less than we use this formula, less than. Put it in there, you get 2.10. What's the pitch coil body? That was one of those definitions back on springs. So you now put in the formulas that you know, which is the free length, the coils that are effective, the 10.5, not the total coils, 3 times D, and you come up with 0.186 inches. Every one of those problems were from the previous slides that had the red boxes on them for springs. So springs, you're probably going to see several spring problems. They're a great tool, and they're great to beat new engineers over the head with to do calculations on. Okay? Oh. Hang in there, stay with me. I can already see the end of this one. We may be ending early. I'm going so fast. Ugh. I can see why I took my mask off. It would be soaking wet.
There's gonna be a lot of spring materials to reference that shape. I was looking for shapes, but I didn't realize to see shape.
Yeah, I'm not sure what you're asking.
I just didn't, we need to know all of those, or the heavy reference, or if there's like less material for springs.
So Christian's asking a question about comparing Shigley's long table list of materials and what's in your reference as far as the materials are concerned. When it comes to materials, they'll do one of two things. They'll either in the problem state the material is, and here is E and G and so forth. Or they'll say it's music wire. And they won't say anything about the other materials. You need to go to the table to get those other values you're going to need. So it'll be one of those two ways. That's how they put more in there, is they give it to you in the problem as opposed to expect you to look it up in the table.
Okay, we're not, most likely, we would see like a oil quench or something. I remember in Shigley, they had some.
No,
that were-
you won't.
They had some that were more industrial applications.
If they do, the problem will say, you're
It'll-
using an
it'll-
oil quench steel with an E of this and a D of that.
Okay.
Solve this. Now, they won't give you a problem where they don't have that data in one of the other tables.
Okay, sounds good, thank you. I just know Shigley goes into a lot more.
They do.
Because there's a lot more applications.
Yep. All right. Ah, bearings. Yes, let's get our bearings and keep moving forward here. Bearings. This is the language of ball bearing love. You need to know it because they may talk about these pieces. One of the questions could be about the bearing construction. Most all the other questions will be calculations on bearings themselves. Don't forget that that inner ring is called an inner race. We've got the balls themselves. We have a ball race sometimes, not always. This mechanism holds the ball bearings at a certain distance. Not all bearings have them. You've got the outer ring, that diameter you're dealing with, inner diameter on the shaft. This is actually an interesting quick sidebar. When you talk about fits, which I will talk about in a few moments, this is what they're applying them to. Now, you could shrink or press fit one part into another to put a pin or a rod in a plate, which is gonna be permanently fixed. It's not gonna rotate, you don't want it to. And so at that point, you can talk about how much torque could I put on the rod before it slips in the fitting. But every other press fit conversation is really talking about bearings. And if you don't do this right, you ruin the bearings. Oh. Because when you think about it, I take this bearing and I'm going to press it into a casing. So this outer face of the outer diameter needs to fit into a fitting. Then I'm going to take the shaft of whatever it is I'm rotating and I have to put it on the inner ring. And I want it not to rattle. I don't want a loose fit. I don't want a slip fit. I want some sort of interference fit where it just barely catches and then makes all the work happen inside the ball bearing, not between the shaft and the bearing itself. So as a result, as an engineer, when you get to these sorts of things, you have to be very, very careful about how you specify that interference and how much you can deal with before you deform one ring or the other. Because as soon as you deform this ring or the other ring, the ball bearing will not work and it will fail. That's why they are so specific in all the dimensions in the catalogs for bearings, because they're expecting you to figure out that interference fit equation to do the right thing to make it all match up. Go ahead.
How do they get the inner race with all the balls inside the outer race?
How do they push the two of them together?
Yeah, is that also a press fit?
Yeah, it absolutely is. And it's an interesting process where depending on the manufacturing of what type of bearing this is, you're gonna end up heating this up quite nicely, cooling this down quite nicely, and pressing the whole thing together. That's predominantly why the separator, that inner ring right there, is also used, is to hold the bearings to get them in while they're being popped in. Now, other bearings, roller bearings or ball bearings like this, they will not, well, I saw the next slide right here. See this right here, this filling notch? This is how they manufactured it. On one side, the diameter is bigger between the two rings than the other. And this is the area where we were able to pop these two parts together to get the bearing in there. So we had the two parts and we were pressing a whole bunch of bearings in from the other side, they would pop and snapped in. And then I put a filler in there to hold or lock them in. The other way you end up doing it is, and I don't have an image of that one, is the inner ring will have a shoulder. It'll be this sort of thing. So when you're looking from the side there, that inner ring will look something like this. And what they're trying to do is they're giving you the ability to push the ring of the ball in from one side after popping you kind of do a two-step process. You kind of get it halfway in there, you pop the bearing in, and you pop it all the way back in again. And some even look like this.
And none of these bearings are meant to take any serious axial load, correct?
Well, that's interesting. It's a really good question, because in most cases, when we're talking about ball bearings, they're designed to take radial load and not axial load, with a few exceptions. If you notice right here, See this one right here? The wall of these two bearings right here were designed specifically to take some axial load. You see the difference right here, the angle? So I get that fraction of the vector in that direction, only in that direction.
Yeah.
So I can only put the load on this bearing this way, axially, and it will take it and transmit the load between bearing and shaft. Most of these other roller bearings or ball bearings do not, with this other exception, and this is only, as it says on there, for self-alignment. In this case, one bearing is working against the other from a load standpoint to keep this part of the bearing centered inside the bearing's body. So it won't drift on you, whereas these, when they wear, if there's any axial loading, will drift. So now the shaft goes like this. So it's pretty cool stuff. I mean, bearings are just awesome to begin with, to think about how they work and the physical point of contact, depending on how they're set up, but the physical point of contact predominantly is right here and right here. Very, very small. And if you do it right, if you got everything scaled right, it rolls perfectly against those two surfaces. So it has this super, super small contact. And remember, we talked about this in the materials, this stuff. Remember the contact forces? Remember this conversation about the forces and the pitting and the galling that occurs right there? This is why we had this conversation, because that's what this is right here. It's a single point contact force. So if you keep it lubricated, you're great. This is why bearings gall or seize. You load them wrong, you get the forces off a little bit, and you know the forces are extremely concentrated at that one little point right there. Just below the surface in here is where it cracks and flakes. That's why when you look at ball bearings, and they have these little pits in them, throw it away. Next time you do service on your bike, you take out the bearings either in the crank or up in the head tube or something like that. Look at all those bearings. And if you see any signs that the wear and chipping on there, the pitting occurs, throw the whole thing away, get a brand new bearing. It's shot. This is what we do in the industry when we are trying to do preventive maintenance. We put giant sensors on your equipment nowadays. It used to be you had to take the whole equipment apart, take the bearing out and look at it. Not anymore. We put a vibration sensor and a thermal sensor right outside the casing on your bearing. And we can listen to the bearing, and we can translate what we hear as to how tight or loose it is. We run a current through your bearing from one side to the other, and based on the continuity of the current, I can tell you if you have any pits in the balls. Because I watch the wave signal that I'm putting through there, and when I see it break every once in a while, in a repeating pattern, I know you have pits in your bearings. So I can tell you way before your bearing ever fails, it's about to fail. So you can swap it out before you ever get to that point. Oh God, this is so cool. What a great living you could get into just by knowing this sort of stuff and then going out and working out. There's a great company over on Vashon Island that does this for a living, flies all over the world. They're so good at it. There's a small flyaway team. They got a couple of suitcases with all this rig on it. There is equipment in massive manufacturing plants that already has their equipment on it, and it's broadcasting this stuff back to them through the internet. They're monitoring the bearings at something halfway around the world. They're getting ready. Hey, guess what? Turbine number 4, or the production line, those 2 motors you got on the system, you're getting ready to fry 2 bearings. If you want that production line running any longer, you better change them out.
Now, do they sell the bearings, or do they just monitor?
They're just the monitoring. They don't want anything to do. This whole thing, this is an art and science in and of itself.
That would be a little bit of a conflict of interest.
Totally, but this is so involved just making bearings to begin with. Anyhow, all of this is to say ball bearings are something you're going to talk about. Oh, roller bearings are something you're going to talk about. Here's how we deal with axial load. So the ball bearing didn't give me axial load, it gave me radial load. So how do I deal with it? I put rollers in there instead. So instead of having a little ball bearing, I put a roller. Now, a couple of ways you can put it. This is a cylindrical drum you're looking at from the side. Inner race, the outer casing here, and the whole thing spins, and the roller drums, just like the balls, rotate around. Big contact surface. So not as efficient, because there's a lot of more friction in here associated with the contact point. Still one little tiny contact point on the cylinder, but much wider than just the single point on the ball. But when you start orienting the cylinder in different axes, you can now handle all sorts of axial loads. This is an axial loaded roller bearing right here. You can see I just press one into the other. That's how we make these. Pretty easy. but I put one in one direction, I probably put one in the other direction on the other side of the machine, keeps the shaft from moving any direction this way, and it deals with the rotational axial or radial forces as well. So they come in lots of different shapes. As far as the problems you're gonna get, they won't show you these images. If they ask you or give you an image, they'll show you things like these. And then you can do the math associated with them if you need to. But these are called tapered bearings right here. You can see they've got a taper shape to them, different tapers like this for the axial loading. And then these are usually needle rollers right here, really thin ones. Trying to think, I broke one of those once and it was all over the place. This tiny roller kept rolling in every direction. It was a mess. Anyhow, terminology for bearings. So, a bearing fails when it gets pitting, or spalling is the other term for it, of about 10 thousandths of an inch, or 10 thousandths of a square inch, area-wise. The life is the number of revolutions or hours at a given speed for failure. So if that's my failure criteria, I run bearings for a long, long time in my test rig until they fail to that specification, and then I calculate how many rotations I have in it. 1, 2, 3, 4, 5, 6, 7. Dang, I lost count. Start again. 1, 2, 3, 4, 5. No, they have big machines that do that. And they figure that out. As a result, we've now got some data on bearings. Then we do a little statistical analysis. We plot it on a curve. We get something called the, not a normal distribution, but starts with the W. Yes, the Weibull distribution. It's a form of normal distribution. But the Weibull distribution just shows you how many bearings fail at different points. And that gives you essentially the reliability for the application of that particular bearing. I'm talking, well, I think I may have a slide on that. But one of these sort of things. Point of failure, most of them occur right about here. Whoop. Everybody else occurs somewhere else. That becomes now my rating for that bearing, based off all the materials I put in its design and its specification. So the average life is called the median life for 50% of the sample to fail. Half the sample to fail, that's called the median life. Some people call it the average life. These are the terms they use in the catalog that you go to pick a bearing. Catalog rating. So in the catalog, you have something called either C sub 0 or C sub 10, constant radial load that causes 10% of the group of bearings to fail. And that's what they use as their sort of threshold of, okay, I'll sell it to you. Sometimes that term is called the dynamic load rating. There it is right there. The basic load rating, C, not C sub 10, but C, that's the catalog rating for a life of 10 times 6 revolutions of the inner ring. Okay? That basic load rating is a reference that they put in the catalog. This is a calculated value that's based off of that Weibull distribution. All right, so that's the concepts you're using in thinking about bearings and how you're going to employ them and put them forward. The static load rating right there, radial load, static loading, radial load, which corresponds to the most deformation of the rolling, heavily stressed contact of 0.0001 times the diameter. So however big it is. You measure that as far as its overall deflection. And the equivalent load rating, F sub E, constant stationary load applied to the bearing before it deforms. All of those are in the catalog. You'd be given those numbers, then you can use them in other calculations. Oh my gosh, it's a Weibull distribution. I did put it in there. That reliability, so now if I know those other factors based off of mechanical properties, you can then say, what's the overall reliability of my bearing? That's the overall reliability of bearing based off of the differentials, which are the guaranteed minimum or maximum value of the life dimensions. That ultimately gives you that big R over there. You're not going to be able to calculate that. You're going to use the simplified formula. There's the C sub 10, great big ugly formula. When you put it all in there, you can start to simplify it. If R is greater, the reliability is greater than 90%, which, why would you choose a bearing with less than 90%? I want a 14% reliable bearing, please. Oh boy, that's a cheap part.
You sell bearings.
You might want to sell a lot of them, but you won't sell many after the first few go in. So for a reliability of 90%, C sub 10 is equal to C, which is PL to 1/8. P is that design load rating and L is the catalog life. Those are both given to you, come right out of the table. So if you've got that, you can calculate C sub 10. This is just the loading criteria where we're using trying to figure out the equivalent force F sub E, how we figure all that stuff out for the inner and outer ring. Here's the bottom line. That F sub E that I talked about on the earlier slide is based off of this relationship between the X and Y axis loads, whether they're radial or axial loads. And when I, right there, equals 1, when this equation right here, this part of the equation is less than E, I is equal to 2 when this part of the equation is greater than E, so you can use that, but it's all about the geometry of the bearing, like a simple roller bearing that's up there. In order to use that formula, you're given, oh my gosh, another table. So, you know the formula, you just need to go get the values. There are the values right there, based off of the ratios, F sub A over C sub 0. C sub 0 you can calculate right here. So you can stick it, come into the table, you can go get your X1 and Y1 depending on whether the ratios are greater than or less than E. Go grab the right two values, stick in the formula, and F sub E is yours. That's it. That's a straightforward problem. I've seen those come up. Kind of a plug and chug problem. Just need to know the formula, need to go to the table and get the right values. What's after this? Go home? Work? Shop? You're going shopping? What are you shopping for? New car?
No, you're.
How'd you get so much money? Oh, shop. That's right, I'm opening the shop from 12 to 2 for those people in the shop. Dang, what are you doing?
Peeing in the shop.
Oh, awesome. Why would you be anywhere else?
Exactly.
Okay. Callie can't come, he's done.
I mean, that makes me sad.
Actually, no, I don't. We need more.
Okay, let's keep going. Oh my gosh, gears. You mean we're not done yet? Let's do something new. We got bearings, we got threaded fasteners, we got springs. Oh my gosh, line siders and bears. Oh my, here we go. Gears. Lots of different gears. Quick refresher. Spur gears are what most of you are thinking of when we talk about gears. That's this type right here. When you twist them and put a helix on them, we call them helical gears. That's pretty straightforward. If you turn the gear face on a 45 or some angle, we call them beveled gears. And not only can you bevel a spur gear, but you can bevel a helical gear. Oh, this gets so mixed. And then you can do something called a worm gear. Interesting worm gear because you're taking and making the load force come off at 90 degrees. All the other gears, with the exception now of the bevels, are essentially on the same plane, input-output shafts. But when you use worm gear, you can actually rotate it, kind of like you're doing a bevel gear. Bevel gears will give you any angle you want. In both cases, both bevel gears and worm gears, the success of those two is how well fastened or fixed you've got the system. Meaning, this worm gear cannot slop and move in either of these directions, or this whole thing chews itself up and falls apart. And its power transmission capability is toast. Same with these. You've got to keep the alignment, which means that the bearings you use, oh my gosh, it's all connected again. Oh, the bearings you use to hold these together have to be able to handle both axial and radial loads in order to keep the positions pristine so that the meshing occurs and the contact point is right where it needs to be. In the wrong point, it's going to fracture and break the teeth. Bad day with gears. What's interesting is people think about just the initial break. The initial break's really not the worst part. It's the part when the little piece breaks off and gets in the way of other gears and breaks them. That's the worst part. That's why you need to change the oil in your car. Because the little wear products that we're talking about come out when you change the oil. If you leave them in there, they get in between other moving parts, and that's what messes everything else up. This is amazing. Mechanical engineering is so connected to your world. You love it, don't you? You're just going along for the ride, aren't you? It's all recorded there for posterity. Put your feet up. Make it look right in the chair. Here, you got to look comfortable. If you're going to do it this way, go ahead. All the way. Put it up. Cross them. Hand behind the head just a little bit. No! We got it. We're there.
cappuccino, please?
So, gear talk. What are we talking about here? The big items. And some of this is gonna look kind of familiar to you to the degree that we have this thing called the pitch, right here, this pitch circle. All right, we've got the top, or the top land. We have the fillets, we've got the, there's the bottom land. Our addendum and dedendum, are related to that pitch circle right there. And here's we call this the base of the gear over here. Little clip of the video up there will give you more details on the gears themselves. But the key elements of the pitch circle, again, that's a theoretical, a calculated contact point upon which all our other calculations are based, which are related to the pressure angle that occurs as it rolls against the other tooth that it's working on. And the pitch circles right there are what we use to mate gears to one another. That's what you use when you're looking in the catalog to make sure the two gears will match. Okay, they have to have ratios that match up. The pitch diameter right there is the diameter of the pitch circle. So if that's the pitch circle, this is the diameter of it for the pitch diameter. The word pinion, that's the smaller of two mating gears. Let's see, circular pitch P, that's the distance measured from the pitch circle to the point to one tooth corresponding to the point on the adjacent tooth. The module M, weird word, ratio of the pitch diameter to the number of teeth. This is so you can compare gears, one gear to the next. The dimetral pitch is the ratio of number of teeth on the gear to the pitch diameter, or the reciprocal of the module. So when you talk about SI units, the module is called the index. So the dimetral pitch, only US leftover because we don't use the metric system. The addendum and dedendum to be added or subtracted. This is the stuff that's above the pitch circle and below. The depth, the whole depth, that's the sum of the addendum and dedendum. That goes from the top land to the bottom land on here. We've got a clearance circle and clearance, and backlash is the amount by which the width of a tooth space exceeds the thickness of engaging a tooth measured on the pitch circle. So if this is my standard point of measurement, it's how much movement I can get between the other tooth, between these teeth, when I engage the tooth. So, if you've got that language memorized, 71.2% of you have memorized it, I can tell. Then here are the different formulas you need to keep in mind. There's the big P dimetral pitch in teeth per inch. There's the number of teeth N. D is the diameter pitch in inches or millimeter. M is the module. P is the circular pitch. And so here are the formulas for calculating that. These are all fair game. Give it a gear with 58 teeth and these measurements. What is the pitch? Give it a gear with this. What's the dimetral diameter of the dimetral pitch? You can figure it out. And these are just some values for typical ones that you might find on some of the gears that are out there, just to give you context. Now, when you put the gears together, the pitch circles are what touch one another. The pressure line is that contact point between the teeth that is perpendicular to that point of contact. So we remember when we do this, we don't cut teeth like this. They're not rectangles, because these points up here would constantly interfere with the other gear. They would click into one another and never work. So we end up doing that involute pattern, that funky sort of shape that you get out of gear teeth. It looks like a tulip. All right, this curve is traced out by that pressure angle right here between these teeth as it moves. And that's what those arcs are that you see, those blue arcs. As they two move together, if you were to follow that contact point through, that's how we came up with the shape that we get out of gears like that. That's why the teeth look that way. There is one contact point. The pressure angle, by the way, depending on the angle of the tooth right here, the pressure angle is perpendicular to that particular point. And that's what you're seeing here, that pressure line which is going between this tooth and this tooth as they, well, the same tooth as they move. So as, if I watch these gears rotate, that point, if I get my finger on it, go right down that line, and then they would disconnect. So that's that pressure line. And that involute profile right there is designed from that basic circle. And we cap the teeth at the addendum circle of 1/P from that pitch circle. Finally, that tooth spacing is based off of the circular pitch. And so that's what we're talking about. And again, you can see right here on this diagram here, you can see the addendum circle and the dedendum circle and the pitch circle that's being rotated around there, and that's the pressure angle that's put together. Now, the reason I'm telling you all this is because your problems are based off of this stuff when you start working on these things. Now, this problem, again, is more than what you're gonna get on the exam. You only get a piece of this. But here's some classic sort of setups. You got a gear set, 16 tooth. Now I know how many teeth are on there. Pinion, bigger or smaller? The smaller one. It's driving a 40 tooth gear. Duh, makes sense. That's got a bigger gear. The diametral pitch, given, 2. An addendum and dedendum are 1/P and 1/4P. These are the standards that most of them are. The gears are using a pressure angle of 20 degrees. So now I know what that angle is associated with the point of contact between the two. That's helpful when you're trying to do your free body diagrams for those other problems. Why?
Because that's the angle that the forces are gonna be broken up into.
Right, and if you're doing the full-on XYZ free body diagram and you're trying to work on stresses and stuff like that, you have two components. If the angle's 20 degrees, you have two components associated with that pressure. That's why that's an important piece of information for different types of problems, not this one necessarily. Compute the circular pitch, or compute the center distance, or compute the radii of the base circles. Any one of those could be a question you could ask. If I put the two together, what's the center distance? In this case, if the center distance was made a 1/4 inch larger, what's the new value of the pressure angle and the pitch circle diameters? Where all of those formulas I just showed you are everything you need to figure this out. We're either forward or reverse. If you're doing A, there's a little simple formula right there to get your pitch based off the pitch diameters of the pinion and the gear, the two different parts. There's the pinion, there's the gear. I simply plug in the values now that I know about how many teeth and what big P is. How many teeth and what big P is. I've got an 8-inch and a 20-inch diameter. Ah, that's useful. If these are together, the center distance between my two gears, the shafts essentially, is the two distances over 2, 14 inches. What I just determined right there was essentially this distance right here, accounting for the meshing of the teeth as they mesh together with one another. So this is now known as 14 inches in our case. And with a 20-degree pressure angle, the base radii, knowing that 20-degree base angle right there, the base ADI for the pinion and the gear come out to 3.75 and 9.37 inches. That's the base radii that we're using between the two. Straightforward. You just need to go back and use the formulas I showed you on the previous slide. Know what you were asked, know what you're looking for, use the right formula, and work backwards or forwards, whatever direction you need to. If you're trying to figure out that new pitch circle, in this case the problem was if I had the gears and they were not quite aligned right, they weren't at 14 inches, they were a little bit bigger. In this case we said, what if it was a 1/4 inch further apart? What's the problem? They don't mesh quite the same way, so they're going to be touching the tips and the pressure angle is going to be off. What would that pressure angle be? So I reversed the process. I know this is 14.25 now, because I know what the ideal was 14. The other way they give you this problem is they tell you 14.25. They wouldn't make you solve that part of it. So you work your way back, and you know the ratio is this right here. So you've got to do two simultaneous equations. You go through the process of figuring out those two values, reverse engineer that cosine equation that you did earlier for the pressure angle, and you learn that the new pressure angle is 22 degrees. So instead of 20 degrees, we now have a pressure angle of 22 degrees. We're talking about the further out in the tips of the gears. They're not meshing fully. Right? Gear math. Here's the same sort of thing, helix gear. So now we're complicating a little bit. We're not just doing a simple spur gear. They've got that helix associated with it. It has a normal pressure angle of 20 degrees and a helix angle. So you've got two angles on here now. Not just the contact angle, but you've got one in another dimension that's talking about what the helix twist is. You have a transverse diametral pitch, 6 teeth per inch, 18 teeth. You can either calculate the diameter, the transverse normal or axial pitches, the normal diametral pitch, or the transverse pressure angle. It looks like this. Same sort of formulas. Bam, 3 inches, done. B, well, I'm gonna take that and use those two different pitches, the transverse pitches, to figure out that one. That one's the transverse, the normal, and the axial. I can do the same thing for the normal pressure angle that we're talking about, and the transverse pressure angle. Same formulas, you're just using them on the different angles. Now when you put the gears together, slightly different math. Essentially, we're talking transmissions here, people. First gear, second gear, third gear. Grind a few, put it in there, how fast am I gonna go? So, we call them gear trains. So if you're given a train, essentially gears going from 1, 2, 3, and 4, you're trying to figure out what the other one's doing. If I have 2 gears like this, you'll notice a weird nomenclature. 1, we don't talk about the first gear. So, and we're trying to find the second gear, which is 3, from pinions 2, driving, running speed. So if I know this one's speed, what's the speed of that one? Well, the formula you need is based off the ratio of the number of teeth between the two. Number of teeth of 2 over number of teeth of 3 times n sub 2's rotational speed, and you get n sub 3's revolutions rotational speed. The D right here, you'll notice, you can also use the ratio of the pitch diameters. So if you're given pitch diameters, you can figure out the gear map. If you're given number of teeth, you can figure out the gear map. The only difference here from your Shigley book to the reference that you have is that we use E instead of M and N instead of omega. So when you see the N's on here, revolutions per minute, your reference uses the little omega, okay? Only difference, it's the same functional ratios. So the problems will be, given a gear train of, and they'll specify the gear train, and a rotational speed of gear 2, what is the output speed? Mechanical engineers, this is your bread and butter, people. Okay, there's one right there. Go. If I'm trying to go from one end all the way to the other end, you gotta work the ratios out. What do you notice in my math here?
The gears 4 and 5 are on the same shaft.
They are all on the, or both on the same shaft. So as a result, gear 4 and 5 have the same rotational speed. So in the math, I don't have a transition between 4 and 5. Because it's the same as that transition from 3 to 4. Did anyone not catch that? I won't embarrass you, just want you to make note. So what this transmission is saying is this was on one shaft, this was on one shaft, these two were on the same shaft, meaning I was going from the small one to the big one, both rotating in the same direction, and this is on its own shaft. So this is rotating clockwise, this is rotating counterclockwise, these two are rotating clockwise, this one's rotating counterclockwise. Interesting term down there, driven or idler gear. Gear 3 is considered what's called an idler gear. It's just pass through from one to the next. These are changing their speed in some sort of ratio. And over here, that efficiency, the product of the driving tooth numbers over the product of driven tooth numbers. And finally, when it comes to bevel gears or worm gears, or helix gears where you're kind of transmitting power on one axis and changing it to another axis, in order to get your rotations correct, this is just a template to give you comparisons between those. Take a peek at it just to make sure it makes some sense to you. All right, stretch, move around. everything's tired. I'm the one doing all the work. You have your feet up and your hand behind your head and comfortable. I don't know where you got this from, but God. Ready? Gear train back. Here's what one would look like. A gearbox. If you've been in a gearbox and you need a 30-to-1 increase in speed. Whatever my input is, I want my output to be 30 times quicker. While minimizing the overall gearbox size, meaning I want to keep it compact, what are the appropriate tooth numbers for all of the different gears? So since the ratio is greater than 10-to-1 but less than 100-to-1, a two-step compound train would be needed. Now, the only reason you'd know that is after you've done a few of these and you've been told that gears in gear trains, those are the thresholds that have limitations. So keep this one in mind. This is a good one to keep in your back pocket just when you look at gear trains. They're not going to give you something as complex as this problem. Again, the guts of this one are what you're going to get, not the whole thing. If each stage contributes essentially 30-to-1 or the square root of 30, each one needs to give you 5.4772 contribution to the steps of transmission from one to the other. For that ratio, 20-degree pressure angle is very common. They'll tell you in the problem if they have a pressure angle that they want to include. Minimum number of teeth to avoid interference is 16. Now, again, this is something else they'll tell you about that. You can calculate the minimum number of teeth in order to avoid interference based off of very simple tables. The number of teeth necessary for mating the gears would be 16 times the square root of 30, or about 88. So that's the number of teeth overall. Using our gear train formula, I can work backwards. And if the overall train value is E, based off of the ratios of the maximums that I need, would be 30.25. We're essentially saying if I only did it with 2 gears, it would be 30.25. But we want to do something a little bit more than that. And within this, there's a 1% tolerance. We won't worry about the tolerance because they won't go that far. If you needed a closer tolerance, you could actually make the pinion size bigger and work your way through it. Here's where it kind of gets interesting. So we're trying to figure this out. We know that E was 30. What's a multiple of 30? Meaning you're going to pick gear teeth that are integers. You wouldn't guess that something was 5.5 and something else because you don't have 5.5 teeth on a gear. So you're going to figure out a multiple that matches up with that E. 6 and 5. So that means between the first and second gear, 6 and 5 teeth would work. I could do 2 equations with 4 unknowns. I got 2 free choices to pick whatever I want. So I can choose gears 3 and 5 to be as small as possible. Pressure angle of 20, so I could go back and do those 2 comparisons of making from gear 2 to gear 3 would be 96, from gear 4 to 5 would be 80. If I put the overall gear train back into the formula, bam, I come out with 30. So that worked. And that would be sort of the mechanics. You can go through that. Recognize though that some gear trains are folded on themselves. The other problems we've done up to this point have the gears kind of cascaded out like this one. This one is actually folded against itself. But when you recognize what it really is the same problem. This is that gear where the 2 gears right here are both running on the same shaft, so have the same rotational speed. But you can use the diameters if you want, or you can use the number of teeth, but you're simply balancing out the geometry between all those teeth to make them balance in the formulas and equations which you're given. So if you're to try it again, if you were given a gearbox like you see up there, same 30-to-1, and you were trying to figure out those gear teeth in the folded gear, we already came up with a 6 and 5 ratio between those 2. But I need to figure out what the total number is for any one individual one. So now I can put a placeholder in there. Of the 2 smaller gears right here, the free choice should be used to minimize, because we said we want the gearbox as small as possible. So let's make N3 as small as we can out of that ratio over there. And if you put the numbers in there to avoid interference, which we learned earlier, that kind of constrains you on the 16. Don't worry about the interference because they won't ask you that particular detail. They want you to be able to do the ratio math between the gear train. If you put that value in and start substituting through the equation, so you can see we're starting to drop out, and 2 is going to be 96. If I work that back through, I've got N4 and N5 equal 112. I can put the ratio back in there of 5, so I can figure out that N5 is going to be 18.67. Wait, I don't have the gears with fractions to them. So, If this gets you close, then you're gonna round that to the nearest integer. And then work back to make sure that it all kind of balances out. You're gonna make sure that you always get integers out of that because you never have fractional teeth that are in there. So a little trial and error to work backwards to go back and get that other number in there. If I say N3 is gonna be 17, or is it, if I let N3 be 17, then 18 and so forth on, working through. So what I'm doing is I'm recognizing this is a problem. So I'm gonna go back up to N3, or where's my N3? Go back to N3, change that to 17, change that to 18, and see what I can get out of this. You won't be going to this particular effort of the equation. They're gonna give you numbers that work out perfectly. And when you recalculate after using that sort of ratio in there, you learn that, where is it? And 5 is another fraction. You can multiply everything by a factor of 6. If you multiply everything by a factor of 6, now you have all integers, and now your gear train fits. So this is the long version of a problem that you could get. When you finally do the final iteration, there's what the final numbers of gears end up. You can notice we got way bigger than we originally started with, and that was to get integer gears of the ratios. The whole goal of this understanding is a gear train is simply ratios of the number of teeth from gear to gear, all right? Or ratios of the pitch diameter. So if you work those out, you can work any gear train to figure out what is the ratio, or given a ratio, what generally should be the numbers, knowing that, and then they'll say, these two gears have this many teeth. They've done that in order to make the math work out. If you do the calculation and the math doesn't work out, you know you did it wrong. Okay? Gear train math. There's the overall double check. This is a critical step in the overall thing. After all this work, and even when you do the ones in the exam, they'll do a simplified version of this. When you get the final numbers like this, don't just say, I've got it. Go back and double check by figuring out your overall gear train ratio to make sure it comes out to what you originally had. In our case, we were told this. We were given this value right from the start. And that's your check. Then you can, yes, this is most closely to this answer. Then you can mark it off. And this right here also did the same thing, because 3 and 4 were attached. The gears, the number of teeth between the two need to be the same. Okay, so that was gear train math. That was gears and their pressure angles and so forth. This chunk is how much power can you transmit through a gear. And so that power H is equal to the torque and the rotational speed. The pitch line velocity, it's a linear velocity of a point on the gear as it moves to the pitch angle. That's what this is here. That's the pitch line velocity B in this case, the gear diameter and the gear speed. You'd be needing both of those if you start getting asked questions about power transmission between gears. Not rotational speed, but power transmission. And for a spur gear, if you want to use it in customer units or if you want to use it in SI units, it's been pre-done for you. Same formula, just the conversions have been built in. You may have to do a little bevel gear stuff. It's the same concept as the spur gear. You just have to add the angle. So it's not just one plane or one dimension you're working on, you're working in two, but it's the same formulas. Now, when I say same, it's same, but it includes the factor that has to break up that one vector into two dimensions, okay? Other than that, it's all the same as a spur gear. There's that 3-dimension, or 2-dimension, or 3-dimension, depending on which one you're looking at, that I'm talking about, because in a beveled gear, because of that angle that's on there, my forces come in a couple of different directions. This right here is the pressure angle. These two are showing you how that pressure angle changes from, instead of being perpendicular to the axis here, it's off on a different tangent. That's why you have all the extra cosines and sines in the formula. Gears. Well, you can never talk about gears unless you talk about the epicyclic gear. Epicyclic gear. I just think it's the coolest animation someone's ever made. And if you notice the green shaft, how much faster it's rotating than the red rotation, it kind of gives you an idea exactly how cool that gear was when they invented it. I'm waiting for one of you to invent something cool like this. Don't shake your head. You're gonna do it. Somebody's gonna do something cool. Tell me about it. This planetary gear right here is pretty awesome. It's made up of 3 gears. This gear is folded inside out. So this particular one that you see on the ring gear, its teeth point in. This is your other classic gear, spur gear called the planet gear because the planet goes around the sun. Oh, this is called the sun gear. There's no flat world here, people. So it's going to rotate around the other side. There's an arm that attaches. In this particular case, that arm consists of the sort of a tripod between 3 because they put 3 on here. And it allows you for 2 degrees of freedom, so 2 different inputs. You can, in this case, you can notice my outer ring is stationary. That's one input. The input going on the, let's say the red shaft, and then the output is on the green shaft. You could hold the green shaft stationary and make the gray ring rotate. That'll also change the transmission. And so many cars use this, tractors, tanks use this transmission still today because it's so simple and true. You do need the gear train value, the E, just like we did for the regular spur gears, but for an epicyclic gear or a planetary gear, that's the formula for it right there. A is the arm, that's the red piece right there. L is the last gear in the planet, or the planetary train. In this case, my last gear. And N is the first gear, N sub F is the first gear in the planetary train. So first gear, last gear, and the arm. So the arm is essentially this thing right here, that red rotation. And if you wanted to think of it, if you unfolded it, this would give you an idea of what we meant by first and last gear. I can see the end, because I know what slides are. Come on, you'll make it. You will be successful.
Blood flowing in.
All right. Gears, couple of gears example. Again, our gear ratio for the gear train, we use E, they use M. N for the rotational speed, they use the omega. If you were given the first gear N2, 100 revolutions per minute, and the last gear N5 being 0, given an E and unlock the gear 5 and fixed arm, planet gear 4 is going to be ring rotating opposite. What would be the ratio? Well, I go and take the number of teeth for each one. This has got 20 teeth, this has 30 teeth, this has 80 teeth. You can see my ratios, 2 to 4 and 4 to 5, comes out to 0.25. Substitute 0.25 into our big formula back here. There it is right there. I'm solving for N sub A. So this is a classic problem. There's the formula you need, but the value you're looking for is not the one that's sitting over here. It's inside the equation somewhere. That's why if you write down what you know, 20 teeth, 80 teeth, 30 teeth, other ratios, that sort of thing, write down what you need. I'm looking for the rotational speed of A. I know where that's in a formula. You'll find the formula. Now you just need to do the algebra to figure it out. So the arm rotation comes out to 20 revolutions per minute. Clockwise.
It's the opposite direction.
Don't forget, you need to have that on the answer. So don't be shocked when you see all the answers, then clockwise, counterclock. Oh, then you gotta go back and go clockwise. Okay? Planetary math. If you're trying to get the speed of 4, you can go back and do the math back inside the equation, reverse it, substitute it back in, so I can figure out what N4 would be, and it would be 33 1/3, counterclockwise. Right? This is just, so this is just a rotational speed sort of question. Pinion 2 runs at this revolution, that much power in the idle gear 3, 20 degree full depth system. They have a module of 0.25, 2.5. Draw the feed body diagram. This really works with gears. Draw a diagram. I forgot to say that. Draw a diagram of the gear problem. If they don't give you one, draw it. It'll keep you out of trouble. You won't miss a gear in the process. You won't miss a number of teeth. That way you can work on the pitch diameters of the 2 gears. You can find that transmitted load, because this equation right here was given to you, how much load, depending on the type of units. You can pick up the tangential force on gear 2 onto the gear 3 based off of the force factor we just gave you. You can use a little trigonometry to figure out how much is transmitted. If you know how much force is on there, then you can figure out how much force is being transmitted to the other gears. And that's the distribution of the forces off that analysis. If you put it back in and add them all up in order to figure out the X and Y directions, essentially that's your free body diagram again. you can figure out what your reaction force on the shaft. The shaft is pushing back with 491 kilonewtons. So I know that went fast, but it was simply a breakdown of what you see on this image right here. It's a sum of the forces, sum of the moments type equation. Now, teeth, when you go through the teeth, we talk a lot about the characteristics of the metal, the characteristics of the cut, the profile, lots of stuff. And there were these great big ugly equations we talked about when we were trying to derive this stuff. Well, Lewis came along and simplified a bunch of that, and Lewis's bending equation was used to simplify the bending that occurs in the teeth up here, so we can figure out the stress or forces that are inside the teeth when they're making contact against one another. Because now the material properties come back into play. Do you want an aluminum gear, or do you want a steel gear, or a hardened steel gear? And do you want it surface hardened, and so on and so forth? Well, you can figure out what the stresses are on the teeth. Bam! Right with that formula right there. Remember what that is? That's the power being transmitted from the shaft into the gear, and these are the forces associated with it. That ends up being the normal shear or normal stresses that are occurring on your teeth. Like at night when you grind your teeth, the normal stresses. Okay, the Lewis bending equation are simplified and applied. That's what you just saw in the previous slide. There's the form factor to give you the big Y right here. The Y is based on some physical constraints inside the gear material itself. And you're gonna give that Y, that great big Y comes in a table. So based on how many teeth you have, oh, I've got a 30 tooth gear, well then your Y is gonna be 0.38. That's what you stick in here into the formula to figure out your stresses on the teeth. Almost. Okay, belts and chains, sure, belts and chains need to go into the equation. You don't have a whole lot on belts and chains on the exam. They can give you a couple. There are some simple equations that are needed to work out the belt and chain math. They're simplified down to this particular setup. So essentially the sprocket you need, which is a gear, and then the chain that you put on there. You can use these, but you don't have many of these in your handout because they don't have you do a whole lot of that. So I'm gonna go on to welding. Welding. Welding's fun. I've been taking welding class, did you know that? Last 8 weeks I've been doing welding class, and I've done MIG, and I've done TIG, and I've done oxyacetylene, I've done plasma cutting, and this Sunday we're gonna do stick welding.
Which one's your favorite?
Favorite. I like the TIG welding. TIG welding is another type of arc welding, or you're melting things. You're getting things up so hot that they melt. But it's a little bit more like soldering. You have a technique to it that requires you to dab your fill rod in there very gently when you see the pool without blasting a hole through the heat of your thin material. So if you're real patient, it's really nice. It gives you a very pretty weld. If you want to do something quick and dirty, you just MIG weld it. Spatters everywhere.
You
You just attach it.
I
Pardon?
find TIG a lot more difficult than stick welding.
I haven't done stick welding yet. Stick welding, to my understanding, is pretty rudimentary with that long stick, which you can't get a whole lot of accuracy in anyway.
It's hard to get the motion down though.
Yeah, in
That's
order
the
to
trick.
swoop and get the nice sort of layers that you get in there. And but the MIG welding is kind of the industrial catch-all for everyone's sort of purposes. You can do interesting brazing with TIG too, which is kind of fun. Anyhow, welding's a pretty excellent sort of manufacturing process that you want to put into the into your mix. And by the way, the only reason I'm taking the course is the school was smart enough to send me off to the course so I can include it in a new course we're making, which is a fabrication augment to the 345. It'll be 346, where we're going to do some casting and welding and some other things.
That sounds really cool.
Yeah, you have to leave first. You have to go. You have to be gone, and then we can do this.
Yeah, I'm gonna intentionally not graduate.
So here's the deal. It comes in two flavors. It's either pressure welding or fusion welding. In pressure welding, as the name implies, we put the two together, we heat it up, we get some plastic deformation, and the two make a contact point that adheres the two. Whereas in fusion welding, you're going to heat it up to a molten state where you physically can see the metal melt before your eyes. You're going to shove the two parts together and/or add a filler material that fuses inside it as it cools. It makes sort of a new material, and it's a combination of the two. You typically get gas and arc welding. Those are the group we were just talking about here a second ago, Whereas up here, this is called resistance welding. You'll see these in factories where they have two probes like this. They'll stick a couple plates together, and they just step, beep, beep, and they tack it together real quick. That's essentially fusion welding. The reason you need to know those terms, just so you can use them, because what you could be asked on the exam is this eye chart. F3, read it. No, what I'm getting at is all of these symbols talk about the different types of welds that you're going to put at a certain location. And so your goal would be able to use the little cheat chart they give you on the weld symbols to understand what they're looking at, or to do a little bit of math on the weld. These are the classic types of welds that you end up doing, all right? A butt weld like this puts the two pieces together. A lap weld like this puts them lapping on top of one another, and you end up either welding between or on the edges. You can see we've got two different joints here, end joint or that T, that are going to occur, and the forces on there are a little different. The zooming in on that one symbol in the center, this is what the symbology looks like, where it's pointing at the weld saying do a weld here, and then the other symbols will appear up here showing you on which side of the material, on this side of the material or that side of the material, are you going to put a type of weld. The types of welds we're talking about look like this. Whether you're going to put a bevel or a V groove weld, filling up a V groove or a bevel, whether you're going to put a fillet and fill in between the two with filling material, whether you're putting a bead on top of something else and putting a chunk along the edge. So these are the sorts of things you're going to be asked with. These are the codes or the symbols that sit on top of or on the bottom of this line right here. And then these are all amplifications or modifications of that type of weld. Now, in knowing that, you just simply need to be able to identify those and understand what you're looking at, so it's worth looking at it. But when it comes to the welds, the one bit of math they could ask you is, given a butt weld of this configuration with a throat height of H, how much shear force can it handle, or load force can it handle, axial or normal force, can it handle on the weld? And that's the simplified formula for it. In the sacred texts, however, they use the letter T instead of H for the throat, they call it, and they use the letter B instead of L for the overall width. Same formula. You've got that, the formula's given to you, that's what you're gonna use, but that's how you calculate it for weld. There is the shear. So in this case, this load was put under an axial stress. This same weld is put under a shear stress. That's the formula for the shear force, or the shear, shear force. A traverse fillet. So I've got plates that are sandwiched together, and a lap weld essentially is what I'm going to put on here. The throat depth is this triangular distance right here. All right. So when you go and do the geometry for this to figure out what the forces are on that weld, you have to take into account the fact that there are two vectors on there. And as a result, that simple formula has to be broken up in two different dimensions, okay? A normal and a shear force. And the throat thickness is based right here. This is the throat thickness right here that you're trying to do. That's what that trigonometry is down there. So that means you can figure out the stresses on that weld. If you can figure out the stresses on the weld, you can figure out how much force is being applied to it when you simplify the forms. Anyhow, the earlier formulas are on your sheet in order to figure it out. Stay seated, don't break. Because the last piece is fits and clearances. Fits refer to that interference between two parts. So you see the image up there. I have a larger part, and I'm going to shove a smaller shaft of some sort on the inside. So I have a big radius on the outside, a little tiny radius on the inside, and an interference radius, R, big R, that I'm dealing with. I have two different material properties. So you see I have two different moduli of elasticity indications up there for the two different materials. And so I need to be able to understand what type of fit this is, whether it's free running, sliding, whether it's going to be an interference fit, and then I can figure out how I'm going to calculate the interference values and the forces I can put on it. So this is what you're going to be asked on the exam, is one of these two formulas right here. These are in your cheat sheet. The difference, same material, you'll notice the modulus is pulled out of the bracket. Different material, you'll notice the modulus for each of the materials is inside the calculation. That's how they're different. You could use this one formula and put the same value in here. Then you'll notice you can pull the R over E, which becomes E over R. It's the same algebra. Alright, but that's the interference that you need to deal with on that calculation. And specifically for the hole, the maximum and minimum diameters are based off of that differential where they're gonna interfere with one another. And so that's the maximum minimum for a shaft with a clearance fit of D, G, H, C, or F. What is D, G, H, C, or F? Where does that come from? A table. So you'll notice D, G, H, C, or F. These all right here happen to be clearance fits. These are transition fits, these are interference fits. So if they tell you you have some sort of clearance fit, you can use this formula here for those for these calculations. If you have any of the interference fits, you need to use this formula. And here are the definitions for these terms. So all you're saying is, how much is one gonna interfere with the other, and what's that total differential that's in there? The reason that's also important is, once you put one part into the other, the question would then be asked of you, how much torque can it hold before it slips? That's the maximum torque. And it's based off of the coefficient of friction, the engagement length, and the interference pressure. Where do I get interference pressure from? That's right, previous slide.
That's right.
Where is it? Right there. Somewhere, right there. That's where I got the pressure from. So that's how much torque it can handle. Now, the allowances, I don't know why I skipped over this one, but this right here talks about how the differential works. So clearance fit, sliding running fit. Interference fit, it's either forced or pressed, driven into it. And then there's a transition where you either have to push it in or have some light keying in it. And this right here is a great image of understanding that difference of the shaft and how one's interfering with the other. This is worth a look before you do these problems, because we didn't do a whole lot of these in the class, and you definitely will get asked one question on interference fit, or a fit of some sort. And finally, GD&T, that's geometric dimensioning and tolerancing. That's the standard associated with trying to dimension something but doing it dimensionally, meaning graphically. It gives us the patterns for bolts, it gives us the datums, so it gives us a datum reference, and it gives us a geometric reference for measurement, like, is it flat? Is it cylindrical? Is it perpendicular or parallel? Is it concentric? Is it symmetric? Is it positioned properly? Those symbols all get used, those symbols, you need to recognize these because they're gonna give you a drawing and say, what is this? The way it typically works is basic dimensions are blocked. Other dimensions are referenced to the material, and it's either a maximum material condition, this is how much you can have, no more, a least material condition, it's gotta be this much and no less, or I could care less, RFS, regardless of feature or size. And it goes in a little block down here in this sort of format. What's the geometric characteristic? What's that one? Position. Physical position in reference to something else, pointing to the feature that needs to be positioned. It's the value associated with position, in this case, cylindrical value, because it's a diameter right there, M meaning most material condition or maximum material condition. That's the modifier right here. And the datums are at the end. Datum A, B, and C, and D, however datum. Let's look at one right here. This block right here is gonna have two holes bored through it, and the position of those holes are very specific. This hole is going to be position reference, with a diameter of 0.8 in reference to datum A, right here. Forget the B for a second. Where's datum A? There's datum A. So against this wall, that position has to have this position within a 0.8 or 800,000th of an inch diameter position in accordance with these values that you see on the sheet. Now, it just so happens, this part over here, this hole, is based off of not only the datum A, but datum B. It's saying this hole needs to be positioned in reference to this hole's position. It just told you to drill this hole first and drill this hole second. And it just told you where to put them. Now, you will be given an image like this and asked, what does this mean? And you're given 5 or 4 choices to choose from. One more example. This right here, I can tell you, is a cylindrical shaft. Some of you are looking at me like, no way. How do I know? The line of symmetry, right here. It goes all the way through. Ah, cylindrical shaft. You're looking at the profile of the cylindrical shaft. Big one, 2 little ones. The big one has a concentricity alignment with at a diameter of 50 thousandths of an inch in reference to datums A and B. What are datums A and B? Datums A and B happen to be the other 2 cylinders. So they're telling me this one needs to be concentric with those. That's what you're going to get asked and be able to define that stuff. Whoa! You are almost graduated. You're down to the last couple of weeks, which means I have to wish you congratulations and good luck. Because look at all the stuff we just covered. Oh my God, I'm excited.